And lastly today we've got this question which practices stationary waves in pipes. In an earlier part of the question you were given this diagram, so it's once again sound waves. Here's the loudspeaker which is emitting sound waves into the pipe, which is open at this end and initially closed at that end and 0.6 meters long. Okay, pause the video and have a go at this one. And here we go. So it's a sound wave, so remember it's longitudinal, but if we try to draw where the particles are, our diagram is a bit confusing. So instead we draw the amplitude of the particles' oscillations, and so and that leads to representing our longitudinal waves as transverse waves instead, and that's much more easier to understand. So that's what we've got here. And so we're being asked to describe the motion of the particles in this diagram at 0, 0.2 and 0.6. So at 0.6, that's a node, so the particles are not moving at all. At 0, that's an antinode, so the particles are oscillating with maximum amplitude. And at 0.2, they are oscillating but with less amplitude than before. And if you want to be really clever, you say that the particles are oscillating in phase with the particles at 0. So they're always moving in the same direction and they're always the same fraction of the way through their cycle. And for the second part, it's now this diagram, 0, 0.2 and 0.4. So at 0.2 this time it's a node, so those particles are not moving at all. The particles at 0 and at 0.4 are at antinodes, so they both are oscillating with maximum amplitude. But notice that the particles at 0.4, they have the same distance moved, but in the opposite direction, and so they're also always moving in the opposite direction to the particles at 0. And for the last part of the question, the bottom of the tube is opened, so now we're in the open pipe situation, and that means that we're going to need antinodes at both ends and a node in the middle, so that's going to be that diagram. Now in this situation, the 0.6 meters is half a wavelength, so our wavelength is 1.2 meters. In this situation, the 0.6 meters is only a quarter of a wavelength, and so our wavelength is 2.4 meters. So we can see that here the wavelength is half the wavelength there, and so that means that the frequency here needs to be twice the frequency there. And remember, that's because V is the same for both of them. The speed of sound is the same in the pipe in both situations. Okay, I think that's quite a nice little test of your understanding that one.